Welcome back, everyone. Hope the test went okay for all of you. So quickly, let's talk really quickly about the test. So the goal is to hand it back by February 25th in class. So I'll bring all of your tests the Monday after reading week. So the first day after reading week, I'll bring your tests in stacks. I'll hand them back to you. Hopefully your marks will be uploaded before then. But that's when I'll be able to get them back to you. You kind of do want your TAs marking these things slowly and carefully so that they don't make errors. But yeah, and good luck to everyone. Just really quick, I mean, I heard back from a couple of people who did the test. They thought it was reasonable. Can I, just by show of hands, so did you think the derivations were harder or the symbolizations? So hands up if you thought the symbolizations were harder. Okay, and derivations? And about the same? Okay, so it looked like not, so interestingly, there was not like 100% on one or the other, but seemed like symbolizations seemed harder than the derivations. Interesting, okay, good. So we'll use that going forward to kind of calibrate the next couple of tests. It would be nice if they were about the same level of difficulty because they are quite different skills. So, okay. Any questions about that stuff? Oh yeah, I will post answers to the test after the makeup test is written. So I think that'll be the makeup test will be first week after reading week, and I won't post answers until that's done. But once that's done, I'll post answers. Okay, any questions about the test? All good? Not good, I mean, we survived it. We survived it. Yeah, okay. Okay, so good. Things to note, exercise 5 is up. These are all symbolization questions, and they're symbolization and predicate logic, which we're doing today. They're due not this Saturday, but the next Saturday, Saturday just before the end of reading week. So you'll have a good long while to deal with these. Okay? Good? Good. All right. So let's get into it. So we've just finished the first major component of the course, which was sentential logic, the logic of sentences. Now we're moving on to predicate logic, which is kind of the next step in layering. You know, this class is just going to layer complexity on complexity from what you've learned already. So if your brain is doing the thing that it wants to do, right now your brain wants to dump everything that you learned from the first part of the semester because you're done now. You wrote the test, it's done, right? But tell it not to do that because everything that you learned in sentential logic is going to be foundational to learning predicate logic. So all that stuff is still important to know in order to do predicate logic. We're just going to add a couple of bits of complexity onto what you've already been doing. Partly that's bad news because you still have to remember all that stuff, but partly it's good news because you've really acquired some of the hardest parts of logic already. Like learning what a derivation is challenging. It's really challenging. So having got that under your belt, you've got a bunch of what the rest of the course is going to be about under your belt. So if you're not like thrilled with what's been happening so far, but reasonably comfortable with where we're at so far, then you're well on your way to dealing with the rest of the material from this course. We've really got not a whole lot of wild surprises to present to you for the remainder of the course. It's just going to be adding bits of complexity onto what you've already learned. So that's the good news of this stuff. Okay, so what is predicate logic? So what we're going to do is open up the sentence. Previously, we had no finer resolution on a sentence than just the sentence as a whole, or a proposition as a whole was the smallest unit of logic. The cat is on the mat. We would symbolize that as P, and there was nothing more specific that we could say than that, right? So now what we're going to do is increase our resolution. We're going to go into a finer grained analysis of propositions. We're going to separate propositions into two parts, subjects and predicates. So the subject of this sentence, the cat is on the mat, is the cat. What we're saying about that subject is that it's on the mat. The part where you say something about the subject is called the predicate. So now instead of treating the sentence as a whole, as one unit, we're going to treat it as two parts of a combined unit. And we're going to symbolize that. We're going to symbolize the predicate part with an uppercase letter and the subject part with a lowercase letter. So M is a predicate. It says something is on the mat. And C is a subject. It says it's a name for the cat. All right. So the subject of the proposition is the thing that it's about. And the predicate is the something being said about that thing. Okay. This is all like, I'm just putting names on things that you obviously already know. In virtue of speaking any human language, you got this implicitly, so I'm just putting names on it. Okay, so here's what we can do by splitting the sentence up, by having a finer resolution take on the sentence. Here's what we can do now. So previously, these three sentences were just utterly unrelated for us. They were just totally different with no logical relation between them. So Anne can dance. Anne is fun, Anne plays hockey. We would have had to symbolize just those as just P, Q, and R or whatever, and there would be no representation of the similarity between those sentences, which is obviously that they have the same subject. Those three sentences are about the same subject, and in sentential logic, we have no method of picking that fact out. So now we're going to do the following. Suppose that the lowercase letter A stands for Anne. That's a name. So she's the subject of the sentence. A is for Anne. And these predicates, the uppercase letters, are things that we're saying about Anne. Suppose D is the predicate, can dance. So we're saying the subject D, or sorry, the predicate D, the property D, applies to the subject A. A has the property D. Anne can dance. Anne is fun, F is the property being fun, H, the property being playing hockey, right? So now we've got a way of representing the similarity between all of these three sentences. The thing they have in common is the subject, A, and the thing that is different is the predicate, the thing being claimed about that subject. Okay, and of course, we can represent the similarity the other way as well. So if we have similar predicates but applied to different subjects, Carl went home, Ari went home, Denise went home, where H is the predicate, something went home. We're saying about some object that it or they went home, and we're just saying it about different subjects. Okay? So that's the basic difference between sentential and predicate logic. So we're in predicate logic now, where our atomic sentences are no longer just one capital letter. There are these combinations of a capital and a lowercase letter, and that applies a predicate to a subject. And those atomic sentences are true just in case the subject actually has that property. So if it's true that Carl did go home, then the sentence HC is true. Okay? Okay. So a couple of conventions. So we've got some conventions to take on board here. Names are going to get letters from A to H. A name picks out a specific thing. So if we're symbolizing something, we assume that a given letter from A to H picks out the same thing in each case. And of course, a name doesn't refer, not of course, but let me stipulate that a name doesn't necessarily just refer to a person. You're used to names referring to people, places, or things. So you can name, for example, an abstract object. You can give a name to the number 17, or Paris, France, or whatever you want. Any object can be the subject. Again, a name can apply to any object. That object can be concrete or abstract or whatever. Okay. This will be, what the name is supposed to pick out will either be given to you or irrelevant. So you don't have to worry about this bit. And then we've got predicates. They're going to get uppercase letters between A and O. This, by the way, is why, as a matter of convention, we only use letters P through Z for our sentences. A convention which I violated on the test, by the way. I hope that didn't mess anybody up. I used letters, any letters from the alphabet, because I thought it'd be a little bit easier to do the symbolizations. Try to use letters that were related to the sentences to make it a little easier for you. That will be wrong. Going forward, we will consider that incorrect. but I did that hopefully to make it, I hope that nobody locked up and went, oh no, we only use letters P to Z. I hope nobody did that. Okay, so going forward, there is, however, going to be an important difference between letters A to O and P to Z. A to O are going to be our predicate letters. We'll reserve those just for predicates. And P to Z are still going to be our sentence letters. They're going to refer to whole sentences. Okay? So, and again, in predicate logic, we've changed the definition of an atomic sentence. Before, it used to be just one of our letters P to Z. P is an atomic, Q is an atomic, so on. Now, an atomic is, it includes the old predicate sentential logic one, but we add in that another type of atomic is applying a predicate to a subject. Okay. So any questions so far? I'm really just laying out conventions. Okay, good. Now, here's where it gets, here's a wrinkle. Here's a bit of complexity here. So a name applies to a specific object. My name is Corey. The name Corey picks out me. I'm a fairly specific person. But sometimes we don't pick out specific objects when we form a sentence. We have a general sentence. So there are prime numbers bigger than 100. I didn't pick out any specific number there, did I? I'm not saying this is a prime number bigger than 100. I'm just saying there exists at least one of them. As it happens, there's a bunch, but there's at least one. All cats are mammals. I didn't pick out any specific cat there, right? So there's no name being invoked in that sentence. It's a general sentence. Or there are no elephants in this room. A general sentence that doesn't pick out anything specific. So we need some extra machinery for dealing with these general sentences. What we're going to need are variables. So for general subjects, we use variables. Variables get lowercase letters between I and Z. And we're going to use these variables to make general statements in concert with quantifiers. Okay, so this quantifier stuff is where predicate logic is substantially it's substantially more complex than the logic we did before, and therefore substantially more powerful. Just really briefly before I introduce this stuff, I want to address the looming issue of math panic. Okay, so here's a thing that happens to very smart people get this experience. When you see a complex formula that you don't understand, your brain just tells you, I can't cope with this at all. You STEM people, you probably don't have this. You probably have gotten over your math panic. But people in the humanities, I'm going to show you some formulas now that are substantially more complex than things you saw before. And you will probably experience, once again, math panic. Right? This probably happens to you at the beginning of the course. You're like, this is math, I can't, and your brain just says, I can't do this. I'm going to show you some new formulas, and it might happen to you again. The thing is just to ride it out. Just ride it out. You will get used to this stuff. The math panic will subside as you get good at manipulating these things. But don't succumb to math panic is my recommendation. Okay, so we've got two quantifiers. These two quantifiers say some and all. They're called the existential and the universal quantifiers. So the existential is this upside down E, and the universal is the upside down A. This is this logical convention is a product of its time. Back when people used to print things using typesetting, so they'd have a chunk of metal in the shape of an A, and they'd put a bunch of those together and smear ink on them and press them against pages. That's how words used to happen. When they were coming up with this logical system, they thought, what's an easy way to get people able to print our books? I'll use a symbol that's just a regular symbol but turned upside down. So that's how we got the upside down A and upside down E. They came up with a symbol that could easily be printed given the chunks of metal that people already had. So that's why those are like that. Okay. So it's very much a product of its time. It's produced around the early 1900s when typesetting was the thing. Okay, anyway. So these quantifiers. So here's a quantified general sentence. There exists an x such that fx. That's how we read that. The existential quantifier says, and you have the variable out front. So there exists an x. And you're saying there exists some x that satisfies the following thing. X has the property f. When we're reading that, what it's really saying is something like the following. If we go through all of the objects in the universe, picking them up one at a time and asking ourselves, does this thing have the property f? Does this thing have the property f? Does this thing? We're going to find at least one that does have the property f. So that's what the existential quantifier says. There's at least one object in the universe, all of the objects in the universe, there's going to be at least one, if not more, perfectly compatible with there being lots of things that have the property f. There's at least one that satisfies this, that has this property. Okay? That's the existential quantifier. It just says there's at least some things that have this, whatever it is. Then the universal quantifier says something stronger. It says, this says for all x, fx. For all things x, those things have the property f. It says if you go through the entire universe, picking up one object at a time, they all have the property f. Pick up an object, any given object, it's going to have the property f. This has f, that has f, so on and so on for every object in the universe. Okay? So that's the meaning of the quantifiers. There is at least one or all. It's going to be very rare that a sentence like this is going to be true, right? There's very few things that everything in the universe has that property. So we'll show you some more complex ones as we go. But just to give you examples. So suppose the property m is mass, has mass. For all x, mx says everything has mass. Every object in the universe has mass. There exists an x such that mx says there is at least one thing that has mass. Yeah? Okay? We can negate our quantifiers. So we can say it's not the case that for all x, mx. That says it's not the case that everything has mass. That's true, right? There are massless particles. So it's false that everything has mass. There are some objects in this universe that are massless. So it's true that it's not the case that all things have mass. That sentence says if you go through, it's not the case that if you go through the whole universe and pick up one thing at a time, everything will satisfy the property has mass. There does not exist an x such that mx is not the case that there exists something with mass. Well, that one's false, of course, because there are things with I have mass. I weighed myself this morning. It turns out I have mass. So that one's false, right? Okay. Now, you might be tempted to think that these two sentences say the same thing. They do not. Okay, so the placement of the negation makes a big, big difference to the meaning of the sentence. So the first one says, it's not the case that for all things, that's the upside down A, it's not the case that for all things, those things have mass. That's true, because there are massless particles, there are things that don't have mass. The second one says, for all things, it's not the case that they have mass. That says, for everything in the universe, if you go through all the objects in the universe, it's going to be false that they have mass. So you get the difference? One saying it's not the case that all, and the other saying for all, it's not the case. Yeah?
So it's just like not both and both not, right?
Not both and what?
So it's just like when we were dealing with what we were being learning before, so like not both and both not.
Right, right. It's a similar difference between not both and both not. Good, good. That's a nice way of thinking about it. Yeah. Okay, so those are very different sentences, but these are the same. Okay, these two sentences say the exact same thing. So it's not the case that for all x, mx, is not the case that everything has mass, is the same as saying there's at least one thing that does not have mass. Okay? And when we get to derivations using this stuff, we'll have a rule that lets you translate between one of those and the other, called quantifier negation. So first one says, look, it's false, so the following thing is false. What's that thing? Everything has mass. Right? The negation applies to the whole sentence. It says, here's a sentence that's good. Here, I'm gonna say a sentence. It's going to be false. Everything has mass. Right? The second one says, there's at least one thing that the following is true of, that it doesn't have mass. And those things are claiming the same thing. All they say is, it's not the case that for everything in the universe that the predicate M applies to them, that they have mass. Okay? And those are both true. As a matter of fact, in our world, those are both true, right? Because there are things that don't have mass. Those are both true, and they're both true for exactly the same reason. Questions? Okay. These two things are also equivalent. So if I say everything has mass, that's exactly the same as saying it's not the case that there exists something without mass. There's nothing in the, so the first one says, if I go through the whole universe and pick up every object, it's going to have mass. The second one says, it's false that if I pick up every object, there'll be at least one that doesn't have mass. It says it's false that I'll be able to find something that doesn't have mass, which is the same as saying everything has mass. Okay. So again, doing these manipulations will come later. Actually doing these manipulations will come when we do derivations using this stuff. Right now I'm just trying to give you a tour of these quantifiers and how they operate, how they work, and how negations work with them. Okay so far? Okay. Okay, so we've got the quantifiers, we've got the idea of variables. Now we can build more complex sentences out of these things. So far I've just been showing you quantified sentences with one predicate, but we can do this. So here's the general rule. If square is a sentence, then for all x square is also a sentence, and there exists an x such that square or sentence is 2. So for all x, if fx and gx is a sentence. So you can, within those brackets, you can have very complex sentences. There exists a y such as jy and gy, that's a sentence. For all x, if gx, then fa, also a sentence. And so on, and so on, and so on. Yeah? So we can build up complex sentences. Okay. Furthermore, here's another way we can build up complex sentences here. So, remember math panic? Don't succumb. Just because this looks complicated doesn't mean it is. Doesn't mean you can't learn it. Just because it feels complicated doesn't mean you can't learn it. Okay, so we can combine these sentences in the same way that we built up complex sentences out of our sentential atomics, right? So if I have a quantified sentence, I have this quantified sentence. If this thing, then it's not the case that there exists a y such that jy and gy. Yeah? So that the main connective of that sentence is the conditional. Right? Okay. And we can combine, so the second one says, for all x, if gx, then fi, or jb. So you can combine things that are quantified with things that are not quantified. So the thing on the left there is a general sentence. The thing on the right is a specific sentence saying that the specific object B has the property J. And that's fine too. Okay? So we can build up quite complex sentences using these things. Okay. And one last wrinkle. You can have several quantifiers in a row. This is a perfectly legit way of building a sentence. So you can say, for all x and for all y, if y has the property f, then x has the property g. We'll get to this later. We'll get to this later. Okay. So I think those are all the complexities and wrinkles of how to put these sentences together that we're going to worry about so far. I think that's mainly it. Okay? Yeah.
So for quantifiers, they don't need brackets on the outside to be considered official?
That's right. That's right. So the quantifiers could be added one after another. Yeah. Yeah. Any other questions about this stuff? Like, the best way of getting comfortable with this is actually to manipulate these sentences, which will happen when we move to derivations. So what we're going to do for the rest of this class is not that, but we're just going to get used to symbolizing sentences in this notation. So that's what we'll do next. If this is like, I don't know how to work these things, don't worry, you will learn when we do derivations. Okay. Okay, one thing to note here, we're going to have a slight change in our way of speaking about these things. So we're used to talking about the main connective of a sentence. Now we're going to talk about the main operator of a sentence. So connective is a kind of operator, and these quantifiers are also kinds of operators. So those are both types of operators, and it could be the case that what we want to focus on is the main operator of the sentence. So recall that, like before, we said you can only apply a rule to the main operator or the main connective of the sentence. The same idea is going to apply here, but now you can only apply it to the main operator of the sentence. So if the whole sentence is a universal, there's certain rules that you can apply to that universal, but those are the only rules you can apply. If the whole sentence is a conditional, then you can use the regular conditional rules. Yeah? No, you won't be able to do that. You won't be able to do that. So, yeah, no, there's no rule that lets you do that. Yeah. There'll be introduction and elimination rules for the quantifiers. So you can take a sentence and turn it into a universally quantified sentence by a certain set of operations, but there's not a direct translation between, because they're very different claims. So between a general sentence and a specific sentence are quite different claims. So there's not a direct logical equivalence between them typically. Okay. Okay, so just as an example of this, identifying, parsing the main operators. The first sentence, the main operator is the existential quantifier, that upside down E at the front, that binds the whole sentence. So you're not allowed to dig into that sentence and do logical operations on the insides of it until you've dealt with that existential, which is like the main. We used to would have called this the main connective, but now it's the main operator of that sentence. Okay, and in the second sentence there, the main operator is the conditional. Right? So for all x. So there's the antecedent for the second line there, the antecedent is for all x if fx then gx, that's the antecedent. The consequent is, it's not the case that there exists a y such that jy and gy. That's the consequent. And you can use all of the old rules that you were allowed to use in predicate or sentential logic now in predicate logic. So if you have that conditional, that's a conditional, if you have that, and you have for all x if fx then gx, then you can use those two lines modus ponens and get the consequent there. Right, so you can do the standard manipulations that you're used to if the main operator is, for example, a conditional. So if the main operator is a conditional, you can do modus ponens, you can do modus tollens, that's stuff that you're used to. But so you're not allowed to do, for example, on the top line, the first one, because the main operator is the existential, you're not allowed to say, well, I have fx, therefore I can get not kx. Right? You're not allowed to dig into the inside, just for the same reasons as before. The rules only apply to the main operator of the sentence. Okay, just to preview how we're going to treat these things. Okay, let's get into symbolizing with this stuff. Okay, so symbolizing the existentials is fairly straightforward. Not fairly straightforward. Relative to the universals, it's the more straightforward one. So if I want to symbolize a sentence, there is something which is fun and good. Suppose F stands for is fun and G stands for is good. Here's how I do it. There exists some object such that Fx and Gx. So there's one thing, there's at least one thing in the universe that is both fun and good. Oh, you better hope that's true. Whew, okay. All right, so, but fairly straightforward, right? None of this should be blowing your mind. We're just saying there exists at least one thing that has both of these properties. So when we're going around picking up objects and asking whether they satisfy it, it's got to be the same object. This isn't true. If there's nothing that's both fun and good, there are fun things and there are good things and they're just different. Some kind of horrible Calvinist worldview. Then this is false, right? It has to be one object that satisfies them both, and then the sentence is true. Yeah? Okay. And then you could say there is something which is fun or good. That's just, if there's any object that either satisfies F or it satisfies G, then the whole sentence comes out as true. Yeah? So existentials, is very typical to try to symbolize these as just series of conjunctions or disjunctions. That's the standard kind of canonical form of these symbolizations. Okay. Now let's do universals, because this is slightly trickier. So we want to say all of a certain kind of thing has a property. We use a universal quantifier and a conditional. So if we're going to say something about a category, we do a universally quantified sentence that contains a conditional. So that looks like, in general, it looks like the following. The antecedent is the category that you're saying something about, and the consequent is the property that you're attributing to that category. Okay. So, all cows are mammals. So I want to symbolize this sentence that says everything that's a cow is also a mammal. All right? So what I'm going to do is put the subject of that sentence, the thing that we're talking about, of the category of all cows. So we put that in the antecedent for all x. If Cx, then Mx has a property of being a mammal. Warm-blooded, kind of furry, live birth, lactates, so on and so forth. Yeah? Okay. So notice what this sentence does. What happens to this sentence if you plug in, so it says, if you go through the whole universe of things, this sentence is going to be true of them. So I pick up my mouse, and I say, if this is a cow, then it's a mammal. Well, is that true or false? Remember the material conditional? It's true, right? Anytime the antecedent is false, the whole conditional is true. So if this is a cow, then it's a mammal, is true. Weird, but true. It really only gets tested when you find something that is a cow. Now the consequent has to be true as well, right? If you find something that's a cow but it's not a mammal, this whole sentence comes out as false, right? Okay. So that's why we do this with conditionals. What you definitely don't want to do is do this with a conjunction. So if I say for all x, Cx, and Mx, then I'm saying everything in the entire universe is a cow and a mammal. That, I assure you, is false. So that's why we use the conditional, not conjunction. Okay. Now, let's add a couple more layers of complexity to this, because we can get more specific about both the category that we're talking about, and we can get more specific about the thing that we're saying about that category. Yeah, said that. Okay. So what if I wanted to symbolize all tired dogs are sleepy? Okay. So we've got two parts. The category is not just all dogs, and it's not just all tired things. It's all dogs that are also tired. So Suppose A is being tired, B is being a dog, and C is being sleepy. So we can restrict our category more than once. We do that as follows. For all x, if x is tired, then if it's a dog, then it's sleepy. Right? So the first conditional restricts it to just this topic of all tired things. The second one restricts it to all dogs, and so we've restricted it to all tired dogs. We say if something satisfies both of those, then it's got to be sleepy. Okay. And an exactly as good, exactly equivalent way of symbolizing that is just to put both of those conditions into the antecedent. We say if something is a dog and it's tired, then it has this property of being sleepy. Okay, so you could pack a bunch of conditions into the antecedent to get your topic more and more specific. Okay, here's what you definitely don't want to do. Don't do this. So the difference between the top line here and this is just the placement of the brackets. So where you put the brackets matters a lot here. Matters a lot. This says if it's the case that if something is tired, then it's a dog, then it's sleepy. Okay, but if something fails to be tired, sorry, the example here doesn't work. I should have done it the other way. Sorry. Does it work? Well, it's still wrong. It's still wrong, but this sentence here it doesn't make sense. So, okay. Does it? Okay. Okay. All right. Good. Good. Okay. So anything that makes A false. If something's not tired, then that whole first part comes out as true, right? Right? The antecedent comes out as true. If you say, here's so suppose I'm not tired. Then that antecedent comes out as true. No, I should have done it the other way. It makes a better example. No, this makes a better example. Should be bx then ax. I'm telling you, this is better. Okay. Because now the sleepy cat thing works. It's just a confusing, it's still wrong, but it's just a confusing way of presenting the example. Okay. So, now, if something is a dog, then it's sleepy, then it's tired. So, if something fails to be a dog, for example, if it's a cat, then that first part comes out as true. If x is a cat, the antecedent is true, because anytime the antecedent of a conditional is false, the conditional is true. So this thing, if bx then ax, comes out as true if our object is a cat. But if the cat turns out to not be sleepy, then the whole sentence comes out as false. Sorry, a non-sleepy cat. Okay. I apologize for the on-the-fly editing of but okay, so you got a cat that's not sleepy. And we ask, so we're going through the whole universe and saying, does this whole sentence apply to everything? Because it's universal, it should apply to everything. There's a cat, and it's not sleepy. So if this thing is a dog, then it's tired. Well, it's not a dog, so that conditional comes out as true. Antecedent is true. But suppose your cat is awake. It's 4 a.m., so your cat is very lively at 4 a.m. Your cat is awake. It's not sleepy. So your awake cat makes this sentence false, because the antecedent is true, but the consequent is false. That's not right. right? You were trying to say something about dogs being sleepy and tired, right? So the existence of an awake cat shouldn't make your sentence about dogs false. So this is not the right way to, this says something, it just doesn't say what we wanted it to say. How do you fix that? Well, you don't put the brackets around the, you put the brackets like this. You put the brackets to the right rather than to the left. That's what fixes this. Yeah? Questions about, I see people still processing this. Questions about this? Okay, so in general, you're trying to restrict the topic of conversation in two ways. The way to do it is either to have a series of conditionals with the brackets to the right, or just do this conjunction thing, where you just pack it all into the antecedent. Okay? And then this thing is wrong. This is no good. Don't make the antecedent of your conditional itself a conditional. Make the antecedent either an atomic or a conjunction, and then the consequent is the subject. Okay. One last thing to add on here. We can make the thing we're saying about that category more complex as well. So if I wanted to say all tired dogs are sleepy and cute, then we do that by just making the consequent a conjunction. We say, if, oh, I'm missing a conditional there. Apologize again. I was sleepy when I did this, but it was not cute. Okay, so if something is tired, then if it's a dog, then it is sleepy and cute. Or if something is both tired and a dog, then it is both sleepy and cute, right? So you can have a complex antecedent and a complex consequent, and you'll do that if there's more than one thing that you want to narrow down the topic on, and there's more than one thing that you want to say about whatever your topic is. Okay? So I hope you can see the symbolization of these categorical statements, these universal categorical statements, is a little bit trickier than the existential one, but is nonetheless highly manageable if you just keep this thing in your head about the topic is the antecedent, and what you're saying about the topic is the consequent. Just keep that in mind, and your normal sentential symbolization skills should carry you through. Okay. Really briefly, I'm very sorry I forgot to load Logic 2010 before doing this. I want to show you just one or two examples in Logic 2010 just to get the controls clear, because there's minor differences between how it goes in sentential and some predicate logic. Okay, so we'll do 3.003 just because we really don't have much time here. We had to bring you an important message before class today. Look how much stuff you know now. Look, you can do all of this. You can do all of this. Okay. Okay, 3.003. Something is good. All right. So once again, you're just right-clicking on this thing, and the difference is you have to say, so if I'm saying there is something is good, that exists at least one good thing, right? So it's an existential generalization, and I'm going to say about that existential generalization that it has a, so there exists at least one thing with the property of being good. So I look at this list on the left here. Oh, sorry. That's off the side. Okay, so I'm looking at this list to find my predicates. This F1 stuff should strike you as a little bit ominous, because later we're going to do two-place predicates and three-place predicates. That one just indicates that this is one-place predicate. Don't worry, that's after the next test. So I find the one that I'm interested in. Something is good. F means goodness. So now I'm going to say that that's an atomic. So Fx is our atomic. Before the atomics were just one letter, now they're two letters, right? And you need that variable that you're typing in to match the variable that Logic 2010 auto-generated for you. Okay? So that should be correct. It's off the screen, but you can. I assure you that that was correct. Okay? So just a couple differences there, just that you pick universal or existential, and then the atomic that you type in is got 2 parts to it. So that should be enough to get you through those exercises. If you need any help, jump on Quarkus, and we'll try to help you. Okay, thanks everyone. Have a good reading week.